Hi guys, sorry about that. Some issues. Now you can see my screen. That's good. Okay. So if we consider some cylinder with a piston which can move back and forth, then by providing certain vibration to this cylinder, it's possible to create so-called compression areas in the air inside this cylinder, and rarefication, like dense regions with higher and lower pressure. So here we have compression, where these three lines are, and in between we have some lower pressure regions. Obviously, if this mechanical vibration will be periodic, so that will be also periodic pattern of high and low pressure inside the cylinder. So if we consider lot of pressure versus, let's say, axis x, we will have something from low to high pressure, low pressure, high pressure, and so on. So if we consider also some small element of air inside this cylinder, because of vibration of the piston, it will also move back and forth parallel to the propagation of the sound wave in this cylinder, means along axis x. So that means we deal with, as you guys mentioned before, longitudinal type of wave, and our like displacement as a function of position and time for some element of the medium where this sound wave is propagating, will happen not in y direction, but in x direction. So that means we will have our wave function, which provides the information on the displacement along axis x as a function of position x and time t. So as opposite to our previous case when we considered y as a function of position and time. So that's why we can write that for this displacement along axis x, let's call it s as a function of x and t, we can actually use the same form of the wave equation. It will be maximum displacement times cosinus a x minus omega t. Obviously, we can add also the initial phase if necessary. So S maximum is maximum position displacement relative to equilibrium condition, which in our case will be also amplitude value for the displacement. What is interesting we would like to do right now is find a relationship between the displacement of some element of gas inside the cylinder while there is some sound wave inside, and change in pressure. and also get this pressure as a function of position and time. So let us consider such a system. Again, we have a cylinder. We have like imaginary, we consider some volume of gas in this cylinder. And let's consider that there is some, let's say, piston, which pushes this volume of gas to the right as a result of compression. The displacement of left and right edges of this volume of gas will be different. So what do I mean? Let's say this is initial position. And see this cylinder again. So this will be new position of the right edge of this volume of gas. Here will be, let's call it S2, displacement 2. And here will be new position of the left edge of this considered volume of gas. And this will be S1. So as you see, S1 is larger than S2, and that happens because we have some compression of the gas volume under our consideration. This is the gas. So now we can consider the change, like difference in the displacement. That will be S2 minus S1. We know the area A of the cross section of the cylinder. And under these conditions, we can write the change of the volume is equal to delta S times A. So area of the cross section of the cylinder times difference in the displacement of left and right edges of the considered gas volume. Okay, now we, as you remember, we want to find the relationship between displacement and I mean expression for the, first of all, expression of for the pressure, change of pressure in this cylinder when sound wave is moving there, as a function of position and time. So something similar like this equation, but in terms of pressure, not in terms of displacement. And obviously we will get some relationship between the displacement and pressure. So change in pressure, which is P, capital P, is equal, it can be given with the following equation, where we have minus B times delta V divided by V initial. So here B stands for bulk modulus, which relates the change in volume and change in pressure in gases. So this bulk modulus is a property of material, of the gas in our case, and for different gases it will be different. So will possess some value for a particular gas in the cylinder. And V initial is initial volume, which we can express because we know the length of this initial cylinder of gas we considered. Let's call it delta X. And then we can write that initial volume is equal to delta X times A. So now we substitute instead of delta V its expression, and with instead of VI its expression. So we will get delta P equal to minus B times, here will be delta S times A, here will be delta X times A. So A, and like in the numerator and denominator, we can cancel. And if we consider some limit when delta X approaches to 0, so we consider very small volume of gas in this cylinder, then we can write that delta P is equal to minus B times partial derivative of the displacement over position X. So we keep in mind that this displacement is the wave function, which is function of position X and time t. So we take partial derivative of this function over X. So let us write it here. It will be equal, maybe clean this part a bit, delta P is equal to minus B partial derivative over X. And here is our function S versus X and T. So it will be S maximum times cosinus Kx minus omega t. Okay, so when we take this derivative, we will get the following. So we have minus here in front of B. And when we take derivative of cosinus, it will give us minus sinus. So this minus and minus will cancel each other. Then constant S max will be. Time is considered as constant because we take partial derivative over X. And when we take derivative of the argument of the cosinus, we will get K, our wave number. So that means we will have B times S maximum times K times sinus Kx minus omega t. So we got this relationship here. This part stands for delta P maximum. And what is, so we will come back to this relationship between delta P maximum and B times S maximum times K, but that will be a bit late. Here, I would like to draw your attention to the fact that we have here cosinus and here sinus. Means that pressure, like change in pressure and displacement of the elements of the gas when there is some sound wave inside the cylinder, will be phase shifted by 90 degrees. So means that we will get maximum pressure when there is minimum displacement. For instance, let's draw it here for some visual representation. So that is S versus whatever time or position X. Then, yes, sure, I can show previous page. So this is our final expression for change in pressure, and this is equation for the displacement. You're welcome. So since we have cosine, so we start from maximum, go down, then go up. And for pressure, like delta P, some excessive pressure, we will get since there is a phase shift in 90 degrees, we will get maximum for pressure, difference in pressure when displacement is minimum. Then will be minimum change in pressure when displacement is maximum. So they are shifted by 90 degrees, and we see why it originates, because from where it originates, if we take a look at our derivation, we came up to this relationship where change in pressure can be expressed as is proportional to the first partial derivative of the displacement as function of x and t over x. When we take this derivative, we change cosine to minus sinus, and that's where this change, this phase shift in 90 degrees is coming from. So now the second important step in understanding, better understanding of sound is deriving equation for the speed of sound wave. That's important step, which we will try to do right now. Okay, there is a question how we came to this point when we take partial derivative. So if we come back here, so there is a relationship between change in volume and change in pressure. So that relationship is via this bulk modulus B. And then we substitute delta V with delta S times A, means change, the difference in the displacements of the left and right sides of the volume we consider. S1 is larger than S2 because we have some compression of this air volume. And that's why delta S will be not equal to 0. Then initial volume is delta X times A. Delta X is just the length of this considered gas cylinder in our derivation. So that's why we can substitute delta V with delta S times A and VI with delta X times A. Now we see here that delta P is equal to minus B delta S displacement divided by delta X. Now, if we consider a limit delta X approaches to 0, means that we consider very small volume of gas inside this cylinder, this ratio transforms to a partial derivative delta S as a function of X and T over X. So why partial derivative? Because there are two independent variables, position and time, in function which provides information about displacement. And we have in the denominator of this expression delta X. So when delta X approaches to 0, we go to derivative, and we end up with a partial derivative of this equation, which is shown here, and provides us information about displacement of elements of gas at any position X and at any time T. Okay, let us go to the next slide and try to derive equation for the speed of sound wave. So in this case, we also consider some cylinder, a good model system for these purposes. Let's have some piston and some volume of gas. So initially it stays in equilibrium. So we have from this side some force which acts on the, so let's say this is our axis X. So in this, from this side, there is some force which is pressure times area. We can represent it in vector form times unit vector I. And here we should put minus because it's an opposite direction to axis X. If this system stays under equilibrium, then from the left side, we should have the same force acting on this piston, however, in the opposite direction. So it will be I times P times A. So this is the force, and all system stays in equilibrium. Now, let us assume that from the right side, where we have this piston, pressure increased suddenly. We have our cylinder, and let's define initial position of this volume of gas. Then this is our piston. Because of additional pressure from left side, so we can write P plus delta P times A. There is some deviation from this equilibrium condition, and this piston is moving to the right, pushing this air to the right also. So this distance, the piston moved to the right, will represent as Vx times delta T. So this delta T is time interval between the first condition and the second condition. So equilibrium, and this second condition system is out of equilibrium because we have some external pressure. What is important here, that the length of this cylinder with gas, which we consider, will be V times delta T. So delta T is the same as here, but V is the speed of sound. So why? Because we consider that at the right side of this cylinder, there will be still this pressure minus P times A times I, like this force, which keeps the air or gas, and the compression, the effect of this increased pressure from the left side, will not reach to the right side of the air cylinder during this interval of time delta T, because any mechanical disturbance in gas can move with highest possible speed of sound. Means it will take some time delta T to reach the with this disturbance from the left side to the right side of this cylinder, and means that after this interval delta T, it will be just reaching just a moment when this mechanical disturbance will reach the right side of the considered air, like gas cylinder, and everything what is beyond this considered volume, means somewhere here, will be not disturbed. So it will still be at the same pressure as before, because it will just need this time to spread along the air cylinder and reach the right side of the considered gas cylinder. That's why we consider gas cylinder with the length of V, speed of sound, times delta T. And during this time delta T, we have displacement of the left side of the cylinder by Vx times delta T, which is speed of the piston. That happens, it moves because of additional pressure delta P. And this speed, if we consider quite narrow gas cylinder, like small volume, we can also consider that this gas is moving with the same speed from the left side as the piston, because piston pushes it. So that's speed of piston, and we can consider that it also speed of the gas, which moves from the left to the right. Okay, so that is our model. Now, pressure, this external additional pressure will create some force impulse, provide some impulse on the gas element, and in return, the gas element will gain some momentum. So we can write this impulse will be equal to the change of momentum. So here it's small p, it's linear momentum. We remember from our previous discussions of mechanics that change in momentum is equal to the impulse of the force. So impulse of the force, we have some net force, is equal to net force times 2 time interval, delta t. And in our case, that will be equal to A, area, times delta P. So we consider, so here is P, capital P is change in pressure. Let's mark it like this. So it will be there, that's capital. We consider only excessive pressure because it's net force, means we consider only excessive pressure because of excessive force because of excessive pressure from the left side. A times delta P times delta T, and we can multiply it by this unit vector I. Now, we remember from previous slide that delta P, capital P, can be expressed in change of volume. So that is minus bulk modulus B times delta V divided by VI. And that is equal to minus B times change in the volume. We see that change in the volume is because of compression of the air by the piston. So we delta V can be equal to area times Vx times delta T. So we can substitute now instead of delta V, A times, since it's compression, we put minus here because it's negative delta V. So it minus A times Vx times delta T. And what we have in the denominator, so it's V initial. And initial volume is speed of sound, V times A times delta T. So we cancel out this delta T and A. Also, we cancel out this minus because we have before B and in our numerator. And we end up with equation B times Vx divided by V. So therefore, now we can substitute this change in pressure by its expression, and the impulse of the force will be given as A times B times Vx divided by V times delta T. And here we have this unit vector I. Now let us consider what will be from the right side of this impulse momentum equation. Delta small p, which is change in momentum, will be m times delta V. M is mass of the gas, which we consider, times change of its speed. So we will have raw density, like volume density, times initial volume. And then what we have Vxi minus 0, because it was under stationary condition, was not moving. Then it started to move with this speed Vx of the piston. And since we assume that the volume is very small, then we can consider that whole volume of the gas is moving with this speed Vx. So in that case, it will be equal, assuming that we can also substitute VI with its expression V times A times delta T, it will be rho times V times Vx times A times delta T. And that is multiplied by unit vector I. So now we have left side and right side of our equation. Let us put it together and see what we get. But let's maybe clean some part of our, we don't need this image anymore. This drawing. So we can write that A times B times Vx divided by V times delta T, that stands for the amplitude of the impulse, I, is equal to rho times Vx times A times delta T, which stands to the magnitude of the change of the momentum. And now we cancel out Vx, A, delta T. So eventually we get expression for the speed of sound equal to square root of B divided by rho. And this is our equation which we wanted to derive, which gives us speed of sound in the gas. We see that it's kind of very similar to the speed of wave on a string. So that was V equal to square root of tension divided by linear density, mu. So that is the general feature of these mechanical waves, that it is proportional, like speed of wave is proportional to some elastic properties. So that defines how like properties of the gas, and also some inertial properties, means density of the gas. So that is true also for solid materials, not only gases. It's just different, not bulk modulus, but some other characteristics are taken into account. And this is general equation which can help us to calculate the speed of sound in different mediums, depends on the elastic and inertial properties of the medium. Another thing which I wanted to mention, that speed of sound depends on temperature. And let's say if we consider our atmosphere, so speed of sound in air can be represented by such an equation as a function of temperature. 331 times square root 1 plus temperature in Celsius divided by 273. So actually, no, I guess it's temperature in Kelvin should be. So if we look at this equation, it's clear that speed of sound increases. No, it's actually in Celsius. So let us put here Celsius, degrees Celsius, because at 0 degrees Celsius, we get 0 divided by 273, so it will be square root of 1. So we'll get speed of sound 331 meters per second. And if temperature increases, then speed of sound will increase. So at 20 degrees Celsius, speed of sound, which is kind of room temperature, will be 342 meters per second. Okay, so this is what I wanted to tell you about introduction of the sound waves, finding the relationship between the displacement and pressure, like excessive pressure in sound wave. And also we managed to derive the equation for the speed of sound, which can be applied to different environments based on their elastic and inertial properties. So we will continue further trying to derive equations for the intensity of periodic sound wave, but that will be already during our next meeting on Wednesday. If you have any questions, you're welcome. Then thank you for your attention and have a good day. See you on Wednesday.
Thank you. Goodbye.
Thank you. Goodbye.
Bye-bye.
Thank you. Goodbye.
Bye. Have a good day.